Having done the problem where the axis was fixed, let us now move on to problems where if I am given a rigid body and I hit it with a force, its center of mass could move according to dP Cm divided by dt equals force external, but also because the forces are distributed over the body itself could change orientation as it moves. For simplicity to start with, we will be confined with motion where axis moves only parallel to itself. For example, it could be a rod on a horizontal table being hit by a force here, then the axis would move parallel to itself, the axis would be perpendicular to the table, and also the axis moves with constant speed or could accelerate. We want to see how to describe the motion of the rigid body in this case. So, let us take a rigid body, apply say force here. One thing is very clear, that the center of mass moves according to this equation that we had already derived. What about the torque? There is a torque about any given point which is not in line of the force, and this should be equal to d L dt about that point. Let us call this point O. Could O be any point? Should O be Cm? Should O be a particularly point specified by certain conditions? We do not know, but we do wish to apply this equation to describe its orientation change. This equation we know for sure describes the motion of the center of mass. Usually you must have seen in your 12th grade or so that O is taken to be the point center of mass, but why? That is the question, and that is what we wish to answer now. Remember, our goal is to apply dl over dt equals tau only external when a body is moving. So, let us take a general point O and a body that is being applied by several forces, and let us calculate the angular momentum L about O. This by definition is going to be summation mi Ri with respect to O cross Vi with respect to O, where I is some general point, and therefore dLO dt, and so far we have been doing that when we take the first derivative dr over dt, that gives you 0 when crossed with velocity. So, it comes out to be summation mi Ri with respect to O cross d Vi O over dt. Let me show you, this is R I O, this is R I, that is the coordinate of the point with respect to an outside origin, and this is R O. Now, V I with respect to O is nothing but velocity of ith point with respect to outside point minus velocity of O, and therefore d V I O over dt is going to be equal to d V I over dt with respect to outside point minus d V O over dt, and therefore we get d L O over dt, that is the rate of change of angular momentum with respect to point O is equal to summation I mi rio d vi over dt minus d vo over dt, and I have forgotten to put a cross sign here. Let me remind you again, this is my reference frame, this is my body, this is point I, this is some arbitrary point O, this is RO whose derivative gives me VO, this is RI, and this is RIO. dvi dt is equal to acceleration of point I with respect to the outside point, which is an inertial point, and therefore mi times this is Fi external, and therefore I can write dLO over dt is equal to summation RIO cross Fi external minus summation mi RIO cross, this is nothing but the acceleration of point O, acceleration of point O. So, what we have obtained now is that the rate of change of angular momentum when angular momentum is taken about an arbitrary point O, which could be in the body, which could be accelerating or anything, is equal to summation I RIO cross Fi external only minus summation I mi RIO cross acceleration of point O itself. This by definition is the external torque with respect to point O, no matter what the point O is doing. So, this is tau external with respect to point O minus AO is a constant as far as summation over I is concerned, and this is nothing but m times r of Cm with respect to O. So, if I want that dl dt be equal to this only, this term must vanish. Let me remind you again what we are doing. What we are doing is we are taking a rigid body, taking an arbitrary point O on this, applying some force on the rigid body, calculating the torque due to this force with respect to point O. Point O could be accelerating, moving, whatever, and then when I analyze this, what I find is that dLO dt is equal to tau external minus m r of Cm with respect to O cross acceleration of O, and I want this term to be 0. I want to choose this point O in such a manner that the last term vanishes, so that with my eyes closed I can always apply dL over dt equals tau external only. This would vanish under three conditions. Number 1, R Cm O itself is 0, and that would be the case if O, the point itself, is center of mass. And this is what you have been doing in your 12th grade or whatever, that you have been taking talks about center of mass and have been applying dL about Cm divided by dt is equal to tau external about the Cm, or this should be about O. Number 2, acceleration of point O itself be 0, that means O is moving uniformly. And third, that acceleration O be parallel to RCM O, that is the point O is accelerating towards the Cm itself. This also you have been doing in your 12th grade. For example, in a wheel which is rolling, you usually take torque about this point and apply dL dt equals tau. This point is actually accelerating towards the Cm, and therefore your answers come out to be correct. So, there are only 3 points in a body in which case this term vanishes, and I can apply with my eyes closed that dL O dt is equal to tau external about that point. We will take a few examples using this equation. So, what we have learned in general, and so far I am restricting myself to only that motion in which the axis moves parallel to itself, that d L about Cm dt is equal to tau external only, no other forces need to be taken into account, no pseudo forces or anything can be applied safely, and the motion of the center of mass itself is given by d Pcm over dt is equal to F external. These two equations are sufficient to describe the entire motion of the body, in that how it is translating, that is given by this, and how it is changing its orientation is given by this. As a first simple example of this, let us take a rod uniform of length L, and let us hit here with an impulse J. Impulse, as you would recall, is nothing but integral f dt, where f is applied for a very short time. So, this is a very short time delta tau, let us say. By the momentum equation, you get that the momentum gained by the rod should be equal to Pcm equals J, and therefore m v Cm should be equal to J. So, after the rod is hit, its center of mass should move with this velocity. How about the omega that it obtains? As we have already seen, I can safely write, let me do it right here, that the angular momentum it obtains about the center of mass should be equal to the impulse, torque impulse that it gains about the center of mass, and that will be J L over 2, and therefore m L square over 12 times omega should be equal to J L over 2, ends up getting omega equals J over m L times 6. So, it rotates as it moves with this angular speed, and it moves with this center of mass moves with this speed.